Welcome to our today's session. So actually the objective of this session is basically that we want to give you the demonstration of the MEMS sensor design analysis and simulation perspective using an industry oriented or basically industrial flavor based or practical fabrication aspect based software tools which is called as CoventorWare. Okay. So by this last couple of modules, we have learned about the various kind of sensors, actuators, their working principles, their characteristics, different kind of specific sensors, actuators, how the construction looks like, what kind of interfacing circuits are required. So those aspects we were discussing. Now we want to have some that hands-on or some actual that design simulation analysis perspective as well. So for that purpose, we thought that this will be a good platform to give you an exposure to the industry-oriented sophisticated tools like CoventorWare, which are widely used for designing, analysis, and simulation of MEMS-based sensors, actuators, or other kind of devices, right? So since this particular license is very sophisticated and it is quite costly as well, so we have one license versions for this in a dedicated computer in our lab. So that's why that it would be convenient so to take it in online mode because that is that CPU specific license, CPU locked license you can say. So that's why that that demonstration is better from that PC itself. Okay, so that's why we preferred to give it the demo in the online mode. And so in today's talk, today's discussions, what we have thought of that in the first around 1 hour or so, we will discuss or continue the last lecture part where we have stopped before mid-sem, and then give you some glimpses and some ideas related to the subsequent portion as well as the mid-sem question answer session. And after that, in the second half of this sessions, we will discuss about the these demonstrations with the CoventorWare software. Okay. So since one part, we could have taken this part offline or as well, but one part offline, one part online. So that would be inconvenient. So that's why we thought that let us take it in the online mode. And in the next week, when we will again that take that regular offline session. So there, whatever the portions I will be discussing today in the online session, that again I will repeat those things quickly in that next week offline session as well. And also these particular sessions will be recorded for your convenience so that you can access later on as well. Okay. So I hope the objective of our today's session is clear to all of you. Okay. At any point of time, if you have any doubts or any questions, please feel free to ask. Okay. So I hope you can that see the screen right now. Just we are sharing, so I hope you can hear me clearly and you can see the screen also clearly, right? Yes or no?
Yes,
Hello?
sir.
Okay, fine.
Yes, sir.
So in the last class before mid-sem, we have basically discussed about this active filter. We have derived both the filter expressions, that output by input or that gain or transfer functions. And we have also discussed the design perspective, that I said the example that if I want to design some filter with cutoff frequency 100 Hz and gain of 100, then what should be the approach, how to proceed it. So those aspects in detail we have derived. Then we have also discussed about this Salenki architecture configurations, which is a second order filter. This left one is the low pass and this is the high pass configurations. After that, we have discussed this band pass and band stop filter as well, which can be realized using one low pass and one high pass combination. And the third one is just the inverting amplifier block. And this one, in this case, we have discussed that is for the band stop filter. Both these we have discussed in detail in the last class before the mid-sem, right? And related to this band pass filter, we have discussed that if I want to design some band pass filter with the gain of suppose 100 Hz to 500 Hz, that cutoff bandwidth of 100 Hz to 500 Hz, and gain of suppose 100. So then how to proceed? So that aspects also we have discussed in the last class, right? And in the similar line, we have given one questions in your that mid-sem paper as well, where you are supposed to design the band pass filter using this kind of configurations. Every details were given. You were that 3 op amps you can use, and the values of capacitance was given. This gain is unity gain, individual op-amp or individual filter. So this is your high pass filter. If you choose both this as R1, this as R1, the gain is the static gain or steady state gain is 1. Here also if you choose this one R2, this one R2, steady state gain is 1 itself. And this one will give you the required gain by choosing the proper value of R8, B and Ri. Right? So in this line, we have given the one questions in the mid set. So we'll discuss that part. Okay. So after that, we have discussed on this PWM generator as well, using which we can generate the PWM signal, which can be used for driving your motor driver or motor control kind of applications. After that, we have discussed the generic aspects, the starting from measure end to sensor. Then we need the signal conditioning block, signal processing block. We need ADC, which will convert the analog data into digital data, and further that digital data can be processed in your digital signal processor or DSP board, and then it will be further connected through DAC to get the analog output, which you can use for some driving some motor or some other kind of actuator. Right. And after that, we have discussed about this ADC and DACs. We have defined their terminologies, their applications, their roles, their fundamentals. And then we discussed in detail about the successive approximation type ADC, its constructions, how is it working, what is the typical conversion time, what is the typical available commercial IC. So those aspects we have discussed, along with the schematic examples for 3-bit and 4-bit, how the steps look like. Right. So this is kind of the binary search algorithms kind of concepts, where we see that if I have n-bit ADC, maximum n clock period is required for its conversion, is not it? And that aspects how the steps looks like. So that we have discussed. After that, we have discussed this DAC example as well, and where this is R2R ladder network based DACs we have talked about, and there we have discussed that in this case eventually the V reference is getting affected. Here this is VREF, so this will be we have derived this will be VREF by 2, VREF by 4, VREF by 8, like of that reference voltage will be changed, and effectively all the voltage will be because of those voltage, the current will be passing through the op-amp depending on whether this particular switch is at 0 position or in this inverting terminal position. So depending on that, either this will be again dictated by what is the bit condition. Is it 0 or 1? If the bit is 0, it will be connected to the ground. If the bit is 1, then it will be connected to this inverting terminal. Likewise, we have derived its expressions in detail, and this is the typical output expressions for this particular R2R ladder network based DACs. Right. So till this we have discussed in the last class, and also in this line we have given one problem in the mid-sem question paper. So that was not directly the same R2R ladder DAC which is given here, but the concepts can be used for analyzing or solving that particular problem, right? So till this, if you have any doubts, you can ask, or else we will move forward. Okay. If no questions, so let us just quickly see that mid-sem question paper. Yeah. So you can see that, of course, that we will give you the detailed solutions or the hints before showing the mid-sem answer scripts. So right now, just I will go through and discuss in brief about the questions papers and the possible answers, and the detailed solutions specifically for the numerical problems or the hints. So those we will be giving later on before showing the mid-sem answer script. Okay. So I hope all of your exams went well. And if you see that the questions as I told, so this will be combinations of some theoretical, some conceptual, some numerical aspects. And you can see that it is not that something completely different from the topics which you have discussed. The questions are not like that. All the questions are, of course, that the related concepts are already covered, and some practicing questions are also given to you in the form of the classwork assignments, as well as in the class also we have derived some numericals and the concepts. So with that, I hope that you should not face much problem. So just let us quickly see. So this defines hyperphysics, that is very standard definitions which was given in the slide itself. The control center role, that is also given in the slide in the smart grid. When we discussed about that, we discussed what is its role for that basically controlling the transmission, distributions, power generations. So those aspects was there, right? So very straightforward theoretical question. Next is again all affine models are linear models. That is statement is false, because for linear models y is equals to ax, and affine models y equals to ax plus b kind of things. Is not it? So only when the b is equals to 0 for the affine model, then I can consider it as the linear model, right? So that is also discussed. Data presentation elements, the examples will be like your display, the transmitter, receiver. So those kind of components or elements can be considered as the data presentation element, which was also discussed in the form of block diagram in our class material, right? Then coming to this that numerical problem. So here this is the straightforward. The thermistor resistance is given. This voltage VR is given. The power dissipation is given. So power dissipation means I square R. The value of R is known. At 20 degrees centigrade, the value is 15 kilo ohm. So then the I is not known. So I square R is 0.9375 milliwatt. R value is known. From there, you have to find out the value of I. Once you know the I, from there you can find the value of R1, because what is I? I is equals to VR by R1 plus R thermistors. So from there, the value of R1 you will be getting around 5 kilo ohms, right? So once you get that value, then simply it will act as the voltage divider. You can easily find that if R1 is 5 kilo ohm, then for thermistor resistance 15 kilo ohm, what is the voltage V1? And thermistor resistance 5 kilo ohm, what is the voltage V1? Right? So that you can find. So that is again at this particular point V1. That is this one, right? Then in the next case, this is a buffer, right? But the buffer is not ideal op-amp based buffer. Rather, it is having some open loop gain of 50. So then what will be the gain? For ideal buffer, the gain is 1, but for non-ideal buffer, this gain will be something like 50 by 51, A by 1 plus A beta. Is not it? So something like that, around 50 by 51, so something less than 1, 0.9 something, the value will be there around that. So this voltage will be multiplied by that gain, and that will be corresponding the output of this particular op-amp, which is as per this number 3. Then in the ADC, the voltage you can find what is the input voltage, and for the ADC output voltage, that reference that is given as 5 volt, and it is 4-bit ADC. So 4-bit ADC means output will be 00000 to 1111. So 0000 correspond to 0 volt, 1111 correspond to 15 volt, that 5 volt basically, right? So from that you can find the resolutions, like you have this that 5 volt divided by 2 to the power n or 2 to the power n minus 1. So based on that, 5 by 15 or 5 by 16 can be the resolutions. So based on that, you can easily find out that the voltage what you have got over here, what will the corresponding the digital output. And if you know that, you can find the dynamic range. Dynamic range, what does it mean? It means that what is the total measurement range divided by the resolution, right? So if you talk about the in terms of temperature, the range is 70 minus 20, right? So 50 degrees is the that span basically, divided by its resolutions. So what is the minimum temperature resolutions it can detect? So minimum temperature means 1 bit ADC output correspond to how much temperature. Based on that, you can find the resolutions, and by dividing that, you can get the dynamic range. Of course, no worry. So I hope that most of you have already done it. But again, for your reference, later on, we will be giving you the detailed solutions. Okay. Then SNR, that is your signal to noise ratio. Signal to noise ratio is given, signal value is given as 1 volt. So noise ratio you have to find out, because 20 log, so this is in dB, that means 20 log of signal divided by noise, that is equals to 60 dB. So that means your signal by noise, that will be your that 1000, because 60 dB and here 20 log of that thing is there. So that is 10 to the power 3, that is 1000. So if it is 1 volt, that will be 1 millivolt, right? So then the straightforward theoretical question, that reference junction compensation scheme for thermocouple is you have to show here. In the next question, this AD5988 IC, that is basically for this, that is the for which sensor, that is for LVDT, right? So that what we have given that there for LVDT, that it is specific use, it is the signal conditioning circuits or IC for your LVDT, right? Then that is straightforward theoretical questions. The pillar type load cell diagram you are supposed to draw and show the orientation of the strain gauge. So two will be along the longitudinal, another two will be in the transverse axis. So likewise, just the two, so two will be along their axis, axial directions. Another two will be the transverse directions or the 90-degree to each other, right? Then again, the theoretical question, hydrogen gas sensors, that is also discussed, and the corresponding diagrams, everything was discussed and given in the lecture materials. Then for the relay also, the circuits you are supposed to draw it, incorporating the diode, which is basically helping to prevent the flyback voltage, right? Then coming to the stepper motor, so the step angle, full step angle we have shown, that is simply that 360 by 8, that is 45 degree, and 360 by 10 is your 36 degree. So 45 minus 36, that is your 9 degree will be your full step angle, is not it? So 360 by 8, that is your 45, 360 by 10 is 36. So 9 degree is the full step angle. And fractional angle means if the two pair of coils are energized at a time, so then it will be 9 by 2, that is 4.5 degree, right? And for this next one, this 160 pulses are applied, how many revolutions? So you know that if the 9 degree is the step angle, so that means 40 pulses are required to get 360 degree. So then 40 pulses means one rotation. So 160 pulses will be 4 rotations, right? So we'll be discussing that later on. Similarly, PT100 RTD, that hints were also given, 0 degree centigrade resistance is 100 ohms. Then what is the value at 120 degree centigrade? Then for that you have to draw the Wheatstone bridge and you have to incorporate the lead wear resistance effect as well. And that was very straightforward Wheatstone bridge problem, which we have discussed a couple of times in the class in the form of classwork, assignments, in the class itself, everywhere. Then the active circuits here, actually that in the class, the circuits where we have what we have used there, we have only considered the RTD without the lead wear, but here I have said that you include the lead wear effect too. So that's why the nonlinearity may not be completely reduced, but you can that completely elimination may not be done, but you can reduce the overall effect. Okay. So then a simple 4-wire RTD configuration, just the schematic you are supposed to draw over here. Then coming to the next questions here, this question 2. In this case, there are 3 cases was there. So all the component values are given. Now case 1 is switch AC is off, Rin is infinity. Switch AC is off means capacitance is disconnected, and Rin is infinity. Rin is infinity means here that you do not need to consider any effect of Rin. And in that case, your open loop gain of the op amp is considered as 120. So if it is ideal op amp, then gain would have been simply minus R2 by R1. But since the gain is finite gain 120, so we have already derived for this finite gain how to do it for the inverting amplifier. Non-inverting amplifier we have discussed in class. Here the inverting amplifier is given. So applying the same approach, you can find out here also A by 1 plus A beta kind of form you will be getting. And because of this finite gain, instead of minus R2 by R1, it will be less than that because of the factor 1 plus A beta. Okay. So in the second case, switch is off. That means C is not connected, but Rin is 400 kilo ohm. Now, if Rin is 400 kilo ohm, then you have to consider that if the Rin is infinity, then what you can consider from V1, whatever current is flowing, nothing will go inside. All the current will pass through this one. While calculating from this side also, from the V0, if you see this current is coming and current is directly going over here if Rin is infinity. But if Rin is finite, then R1 and Rin will become in parallel, or R2 and Rin. So that you have to basically see that what will come in parallel, and here you can apply some nodal analysis to see its effect. And based on that, because when you will apply the nodal analysis over here, then earlier if Rin is infinite, then only this branch and this branch you have to consider. But if Rin is finite, then this branch effect is also need to be considered. And for that, there is a small trick is given. But if you remember, we have discussed in class in board, I have drawn it that if Rin is finite, so then this is acting some kind of voltage divider, so its effect also need to be considered, right? So that was small trick was there. So we'll discuss, share the solutions later on. In the third case, switch S is on, Rn is infinity, but in this case switch S is on means then it will behave as the in that low pass filter you can consider, right? This is R and C in parallel, so low pass filter configurations. So for that, your what will be your cutoff frequency? 1 by R2C, omega C equals to 1 by R2C. So from there you have to find out this that 3 dB frequency, right? In the second case, in the second questions, that this R2R ladder network output is asked. So basically, you know that these voltages are given at this particular point. So either you can apply some nodal analysis and find out what is the voltage at effective voltage at this point. Then you can calculate the gain as per the inverting amplifier configurations, or you can just use the superposition principle. Superposition principle means considering this as 0 and see how what is its effect, and then again in the next consider this effect is 0 and see its effect, then you can add it to get the total current, and from where you can find the output voltage. So we'll be sharing the answers afterwards. Then the third one is that active band pass filter. As I said, that is already the that concepts was already given. The some design problems were also discussed in class. Based on that band pass filter you have to suppose to design it. And the last question is very straightforward questions, where this sample and hold circuit switching frequency is asked for the successive approximation ADC, right? So the sample and hold circuit, that sampling time should be greater than the conversion time, right? So from that concepts, you are supposed to find out what is the maximum allowable switching frequency. Okay, so this is about the question papers. And before showing the answer scripts, we will share the detailed solution. Is it okay? Any questions or doubts from anyone?
Okay, sir.
Okay. Okay, fine. If you have a question, you can ask, or else we will move forward. Okay. So if it is fine, let us proceed. So I hope you can see the screen and you can hear me clearly, right?
Yes, sir.
Okay, fine.
Yes, sir.
Thank you. So now coming to the next concepts. So we'll discuss that few couple of concepts, and after that we will start the demonstration sessions for the MEMS sensor design or sensor actuator design aspects. And these concepts again for your convenience, we are although we are recording it, but again in the next week offline session again we will just quickly recap or highlight the important aspects. And if you need any clarifications, please feel free to ask. So the next concept is sampling and its issues. Okay. So you remember that here when we discussed about this sample and hold circuit, what we said, you remember? We said that suppose this here I have some okay. So suppose what we have said is that suppose this is some time of this kind of circuit is some signal is there. So this is your, if I consider this V in, then through this sample and hold, what we are doing, we are sampling it, right? So sampling means we are discretizing it, is not it? So this value we are discretizing and holding it for a particular moment, and this holding time, that time should be greater than the conversion time of the successive approximation ADC, so that within this time frame the proper converted output of this corresponding analog input voltage will happen, right? If this particular time is less than the conversion time, then we said then proper conversion will not happen, because in that case what will happen, before converting suppose this value is your V1, this value is your V2. So before converting the value V1, the next V2 sample will come into the picture, and because of that your proper analog to digital conversions will not take place, right? So for converting the analog signal into digital signal or discretizing the analog signal, we need to sample it. So sample it means discretize it, right? Now the discretization interval or the sampling interval, whether this time interval will be 1 microsecond or 2 microsecond or 1 second or 1 millisecond, on which basis we need to decide or judge that this particular sampling is happening properly. Okay. So in that context, what we are trying to say over here, that suppose you look at this analog signal is there, this sinusoidal signal is the analog signal. Suppose this particular sampling frequency of this analog signal is 200 hertz. The frequency of this analog signal is suppose 200 hertz. Okay, you can check that. This x-axis is your second. So this is your 0 second, and you can see that from here the time period will be something over here, is not it? So this correspond to the one time period. After that again it is repeating, is not it? So what is the corresponding time? You can see this is 0.005 second. So 0.005 second, the time period. Then what will be your frequency? 1 by 0.005. How does it, what is the value? 200 hertz, is not it? So this is a 200 hertz signal. Now I am sampling it. So sampling it means I am discretizing it. So discretizing at what interval? 2000 hertz. So you can see I discretizing it means I am discretizing like along this, along this, along this, along this. So likewise I am discretizing. So based on the discretizations, I am getting these blue dots, right? I am getting these blue dots. That is what I am doing essentially. I am sampling the signal. Okay. After sampling the signal, what I will be getting? I will be getting these discrete dots, right? Now, what is the objective of the sampling? I want to convert this analog signal into digital signal or discretize it. Why we need to discretize it? Because I want that the after discretizations, I will be getting those discrete points or discrete signals, and then that discrete signal I will be sent to a where I will be sending it to the digital signal processor or some microcontroller, where the microcontroller will that analyze those digital data and do some operation in the digital domain itself. Okay, but finally, why I am doing this analog to digital conversion? Because your embedded system or embedded processor, it do not understand the analog signal. It can understand the digital signal. So that's why I am converting it. And after converting, what I am doing, suppose the filter, if I talk about the filter. So what I do for filter, that if I talk about the analog filter, like what we have discussed, low pass, high pass, band stop. So those filters, what they are doing, they are taking some input of some analog signal, and then they are doing the filtration. So what kind of filtration? So they are removing some unwanted frequency component, right? And then in the output, they are giving the filtered output, which will be kind of noise free output, right? So now if I want to do the same thing in my digital processor, then what I need to do? I need to, the filtering I do not need to do in the analog domain. Rather, I will be sending the raw data in digital form into the digital processor or the embedded processor. And then the filter logic or filter operation will happen inside the processor itself. Okay. So processor, what it will do, it will take the raw data, and that raw data, analog data, it cannot take. It need to be, it will take the discrete data or the digital data, and those data it will be doing the filter operation, apply the filter operation on the digital data. But finally, after doing that, I will be getting the filtered digital output, is not it, from the processor. But the digital output may not be directly useful to drive some physical system or some motor kind of things. So that's why we might require to again convert it into analog signal using the digital to analog converter, so that the analog signal what I will be getting finally, that will be noise free output, and that analog signal you can use it to drive some motor or your whatever systems you want to trigger or drive, is not it? Now here we are doing this analog to digital conversions just so that the digital data can be processed in your processor or the DSP board itself, so that you can do a very high accurate filter operation. Now, in this context, suppose I am discretizing it, and these dots are sent to the processor, where the suppose the filter logic is applied on this discrete dot, and after doing the filtration, I want to convert it into analog domain itself. So now suppose if I do in this way the sampling, if I do, and 200 hertz signal if I sample at 2000 hertz, then you can easily understand I will be getting 10 samples in a particular one time period. So you can just count it. From here, if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And this is just from here. Again, from the 11th one, again, it is repetitive. So basically 10 dots I am getting. Why? Because 200 hertz signal I am sampling at 2000 hertz. So 2000 by 200, that is 10 data points I will be getting for each time period. Is not it? So you can see that if you consider that what is this time gap. So you can see if this is somewhere over 0.001, so this one will be something 0.001 by 2, right? So 0.001 means 1000 hertz, and this will be 0.0005. So that is the time period between this and this, is not it? So this, what is this time period? From here to here, this time period is 0.0005 second, is not it? So what is the then frequency? 1 by 0.0005, that is nothing but your 2000 hertz, right? Now I am discretizing it. After discretizing, I am doing some filter operation. Then after doing the filter operations, suppose this is my fundamental signal. So then after that, if I simply join the dots, if I simply join these dots, if I simply join the dots, then what you can see, after joining the dots, I am getting my original signal back, is not it? Now let us take the second case. In the second case, the solid curve that correspond to your a signal whose frequency is 2200 hertz. Okay. Now this 2200 hertz signal I am sampling at 2000 hertz. My sampling frequency is same. Here also 2000, here also 2000. But in this case, my original signal frequency is 200. In this case, my original signal frequency is 2200. If I do that, then what you can expect? At one time period, how many data I will be getting? 2000 by 2200. So then less than one data point I will be getting in each time period. So you can just check. Suppose if you see that this is your original signal, and when I am sampling it at 2000 hertz, you can see that this is the first data point and the second data point is over here, is not it? So this time you can see this is in one time period less than one data I am getting, is not it? So in two time period, I will be getting less than two data. So that kind of things I am getting. So eventually, if I sample it in this manner, and after sampling, what I will be getting? I will be getting these blue dots, and those blue dots are sent to my digital processor, where suppose the filter operation is happening. And after doing the filter operation, I am again getting the noise-free output of this kind of dots. Now, if we join the dots, let us see if you join the dots, how it will look like. If I join the dots, so then after joining the dots, you can see I am getting this kind of analog signal after joining the dots. Yes or no? Now you can compare. In the previous case, what we have seen, this red line and blue line were matching to each other. So that means after doing the processing, then when I am again converting it back into the analog signal, I am successfully able to reconstruct the signal. But in this case, I can see I am no more able to reconstruct the original signal back. Is not it? Because you can see this red signal is having completely different frequency with respect to the blue signal. Why it is happening? This is happening because of the improper sampling frequency choosing, right? So that's why this particular phenomenon, when the sampling frequency is not proper, then after joining the dot or after reconstructions, I will be getting some low frequency signal, which is of course very low with respect to the original signal, and this particular frequency is completely different from my original signal, and it is showing some low frequency signal, and this particular phenomenon is called as aliasing phenomenon. This particular phenomenon is called as aliasing phenomenon, where after reconstructions we are not getting the original signal back, rather I am getting some low frequency signal. Okay, so that's why to avoid this aliasing phenomenon, what is the minimum sampling frequency I should choose? The minimum sampling frequency I should choose, F sample, that should be greater than equal to twice of my FM, is not it? So if the FM is the signal frequency, maximum component of the signal frequency, so the sampling frequency should be chosen at least 2 times more than the original signal frequency. So here, if the signal frequency is 200 Hz, my sampling frequency should be greater than equal to 400 Hz. Here, if my sampling signal frequency is 2200 Hz, then my sampling frequency should be greater than equal to 4400 Hz, so that I will not have any kind of aliasing phenomenon, and I will be able to reconstruct the signal back after joining the dots like that. Okay, so this twice of FM, that is called as the basically that Nyquist frequency, and for proper sampling and reconstruction, the sampling frequency should be greater than Nyquist rate, that is twice of maximum frequency component present in the signal. Hello? Yeah, someone is saying something? Hello? Okay, so anyway, so now twice of maximum frequency component means what? Here I have, in both the cases, I have one sinusoidal signal with a specific frequency. Now suppose if you have one sinusoidal signal with multiple frequencies, suppose V1 is the signal which is having, suppose, A1 sine 2 pi F1t plus, suppose, A2 sine 2 pi F2t plus, suppose, A3 sine 2 pi F3t. Suppose I have a signal which is having 3 frequency component F1, F2, F3. Then how should we choose the value of Fs? Right? So I have to see out of these F1, F2, and F3, out of this, which one is the maximum? So maximum of, so that is your FM. FM is the maximum of F1, F2, F3. Suppose F1 is 100 Hz, F2 is 200 Hz, F3 is 300 Hz. Then what is your FM? FM will be how much? If your FM is 100, F2 is 200, F3 is 300. So then what is the value of FM?
300.
300 Hz. So 300. Maximum of these 3 components. So then if that is the case, so then if you consider this is your 100, this is your 200, this is your 300, then what should be the value of Fs? That should be greater than equal to 600 Hz. Is not it? So in that way, I should choose the minimum sampling frequency. Is it okay?
Yes,
it is
sir.
fine.
Yes, sir.
Yeah. Okay. Let us proceed further. So yes, again, so here these concepts, some of you might have already exposed to some concepts, but again, for them it will be a quick conceptual aspects, and for the new brush ups, and for the new people it will be that fresh background discussion. So to carry forward further, again, suppose I am choosing this 1500 is my original signal and 1600 is the sampling frequency. So here again I will be getting the aliasing, because for proper that to avoid aliasing, at least my sampling should be greater than equal to 3000 Hz. So here again I can see this 1500 Hz and 1600 Hz. So here if I join the dots, I am not getting the original frequency, right? Here you can see if I join the dots, then here again I am not get, because my original frequency is this high frequency signal, and after joining the dots I am getting the low frequency signal, right? And what is the frequency of this low frequency signal? You can consider, suppose in this particular case, this time period of this low frequency signal is how much? This is x-axis is millisecond, 10 millisecond. So 1 by 10 millisecond means how many? What is the frequency? 1 by 10 millisecond. So that means how many hertz?
0.1 kilohertz.
0.1 kilohertz means 100 hertz. Is not it? 1 by 10 millisecond means 100 hertz. So my actual signal was 1500 hertz, but after sampling with 1600 hertz, I am not getting this 1500 back by joining the dots. Rather, I am getting some low frequency signal which is having only the frequency of 100 hertz. Right? Where from this 100 hertz is coming? Simply, you can see, you take the difference 1600 minus 1500. That corresponds to your 100 hertz. right? So if you have, so this finding the aliasing frequency is very simpler. This is the lowest frequency component. This 100 hertz is the lowest frequency component, but there is a that interesting that mathematical analysis behind this particular aliasing phenomenon, where actually the sampling frequency will be that your this actual, if you consider this sampling frequency, so that after sampling the signal will be something f equals to nfs plus minus fa. So actually there will be the repetitive frequency will be there. The lowest frequency will be where fs is the sampling frequency, fm is the maximum frequency component present in the signal, and n is the integer 1 2 3 4 5, likewise that it can be of any integer. Even the value of n can be -1 -2 -3 also, but since the physically the minus frequency does not have any physical meaning, mathematically it is having the meaning, but physically does not have the meaning. So you can consider the n value is 1 2 3 4 5 like this. And that's why if you consider the value of n equals to 1, if you put the value of n equals to 1, so then your smallest frequency will be fs minus fm. So from where this 1600 minus 1500, this 100 I am getting. That is the smallest frequency component present in the aliased signal. Okay. But mathematically, we can see that there can be not only 100, rather repetitions with respect to this NFS, we will be getting the multiple repeated frequency component in the sampled signal. Now, FFT means fast Fourier transform. This will tell you the frequency component present in the signal. So this dotted line after the joining the dots, if I analyze the FFT of this that particular signal, then you can see in this FFT, I am getting this peak dot peak value at which particular value I can see at 0.1 kilohertz. 0.1 kilohertz, that means what? 100 hertz. At 100 hertz, I am getting the peak. So that means this particular red signal, if I do the FFT, I will be getting at 100 hertz, I will be getting a peak value, right? In all other frequency components, I should get zero value if it is having the ideal sinusoidal signal with frequency 100 hertz. Okay. So sampling below the Nyquist rate cause aliasing, resulting in a low frequency signal instead of original signal reconstruction. Okay. So I hope it is fine. Now, let us discuss with respect to our interfacing circuit point of view. So how to take care about this aliasing phenomena. Okay. So there you can think of two aspects. One is that while doing the sampling, you can choose the sampling frequency greater than equal to twice of FM. If you can ensure that, then you will get the completely aliasing free output. Yes or no? Now, in that case, you should have the provision to get or to apply any kind of sampling frequency as per your desire. But if there is some restriction means, suppose you are choosing a particular microcontroller using which you are trying to generate some sampling frequency, or some device or some circuits for generating the sampling frequency, and suppose that is restricted. That means the maximum sampling frequency can be, suppose if I consider some case where maximum sampling frequency is suppose 1 kilohertz, for example. That means I do not have the provision to choose any kind of sampling frequency as per my own wish. Rather, the sampling frequency is limited to 1 kilohertz. In that case, how can we prevent the aliasing phenomena? Okay. So what I have to do? If my sampling frequency is fixed, then somehow I have to restrict the signal frequency. Yeah. Am I audible? Is there any?
Yes, sir.
Yes, sir.
Yes, sir, you're
Okay. Okay. So okay. So basically, what I said that if my sampling frequency is fixed, then what I can do, if my signal frequency can be anything. Now I have to do some restriction using which I will be restricting the input signal to a particular value. So in that case, what I can do, I can use some anti-aliasing filter. What is this filter? This filter is nothing but insert this filter before sampling, which is nothing but a low pass filter. That means what it will do, this low pass filter I have to use before the sampler, so that the sampling frequency is set at 1 kilohertz. Now the signal which will be going to the sampler, that signal should be restricted to how much value, so that using maximum 1 kilohertz I will get aliasing free output. So I have to restrict the input signal at what value? If my sampling frequency is fixed at 1 kilohertz, tell me.
500.
500 hertz. Very good. So basically that if somehow I can restrict my input signal at 500 hertz, so that's why twice of 500 means 1 kilohertz. So then I will be able to get the aliasing free output. But in that case, what is the trade-off? The trade-off is I am basically removing or omitting some that actual signal frequency, right? So that is the trade-off. So in that context, if you look at this diagram, so that will give you the clear idea. So suppose this is your sampler block where, for example, the maximum fs is set as 1 kilohertz, for example. So this is the original signal which is coming from that some sensor or some device or some system. Then if I connect this original signal to the sampler, then this can cause aliasing if the original signal frequency is going beyond 500. So that's why in between we are putting this anti-aliasing filter, which will be nothing but a kind of low pass filter whose cutoff frequency of this low pass filter, maximum cutoff frequency I can choose as maximum cutoff frequency of FC, that I have to choose as 500 hertz for this example, so that this particular, whatever be the signal, this will be restricted, maximum value will be 500 hertz. So that after passing it to the 1 kilohertz sampler, I will get that dots, what I will be getting after reconstructing, I will be getting the perfect original signal. Okay. So that is the concept behind this anti-aliasing filter. So it will eliminate the frequency component of the original signal which are above the half of the sampling frequency to avoid the aliasing. But this will be having, what is the trade-off? The trade-off is we are removing some wanted frequency component, some original signal we are removing. So that can cause the signal quality degrading of signal quality. If we talk about some image, then from the image, if we remove some original frequency component, then that will lead to the blurring of the image. For example, if the image is basically 2D signal, it is also consisting of multiple frequency components. So if I remove some frequency components by this anti-aliasing filter, which is nothing but your low pass filter, then it can cause you some signal degradation or blurred image, right? So I hope till this it is okay to all. Fine.
Yes, sir.
Okay. Now coming to this integrated sensor system. So by this time we have understood the important aspects with respect to that sensor constructions working, actuator constructions working, their basic interfacing blocks or signal conditioning circuits, including amplifier, filter, ADC, DAC, all those aspects. Now let us take a look of some practical system. So suppose if you take the example of MPU 6050, which is a practical sensor system, and this is the actual IC, which is having the inside this particular IC, you have accelerometer sensor, gyroscope sensors, magnetometer sensors. This does not have the magnetometer, accelerometer, gyroscope, and the temperature sensor. These three sensors are there. Additionally, some processors are there, some IOs are there, some different registers are there, some digital motion processors are there inside this small device itself. Okay, and here this is the development board where you can have different kind of pins are there for giving the power supply, VCC, then ground, then SCL, SDA for your data communications. you have the XDXCL, you have the AD0, you have the interrupt. So these kind of different pins are there. And now using these pins, basically you can take the input, you can use this particular device or the sensor systems for your applications to take different kind of output. Now inside this device, if you look at the block diagram, you can see you have three axis accelerometer is there: x axis accelerometer, y accelerometer, z accelerometer, x gyro, y gyro, z gyro, then temperature sensor. Then as the signal conditioning block, you have the ADC. Before that, you can also have the signal conditioning including your amplifier, so which is basically amplifying or converting the analog into digital signal. Then those digital data is going to the digital part, where you have the different registers are there, different sensor register, configuration registers, then interrupt registers. Here you have this digital motion processors. Here you have the communication block, I2C SPI communication, through which the sensor data can be transmitted from one place to another place through wired medium. You can have some wireless medium as well. Then different kind of low dropout regulator, bias, those kind of circuits are also there. So inside this IC, it is having these kind of different blocks. So specifically, it includes the 3-axis MEMS gyroscope with 16-bit ADC and signal conditioning, 3-axis MEMS accelerometer with 16-bit ADC and signal conditioning, digital output temperature sensor, digital motion processor, gyroscope and accelerometer, self-test. Self-test feature is also there, so that instead of directly applying on the some field trial or some practical systems in the lab, also you can test the device whether it is working properly or not. You have the sensor data registers, you have the I2C SPI kind of serial communication interfaces for communicating the sensor data from one place to another place or from one device to another device. So these kind of aspects, right? So essentially the components, whatever we have discussed so far, all of them are inherently presented or must be presented in this kind of ICs. So where that's why we have discussed in our previous modules, like different kind of sensors, their working principles, constructions, then the different kind of signal conditioning aspects, and both for the sensors perspective as well as the actuator perspectives, including your ADC, filter, DAC, all those aspects. And through these examples, we can see their real utility in the practical device or the practical system. Right now, in these blocks, the other blocks already we are aware of, specifically for the sensors and the signal conditioning part, but the communication part is left. So now we will be discussing about the communication protocol, using which I can connect my sensor output to the processor input, or one processor to another processor. Those kind of communications we can make with the help of the different kind of communication protocol. So that's why now we will be discussing about the communication protocol for this integrated sensor system. Okay. So in today's smart sensor systems, we have, as we said, we have the sensors, we have the signal conditioning and processing block, analog, digital, analog signal processing, signal conditioning, power supply, and then finally we need the communication block through which the sensor data can be transmitted to some other locations or some other processor or other user for their applications or requirement. Right. So in this context, let us look at that what are the different kind of sensor communication protocols are available. Okay. So as we said, smart sensor, that is the built-in signal conditioning, processing and communication block. So for the communication purpose, we have the data acquisition card or the DAC, which is basically very important and very generic system, data acquisition system. And data acquisition means that you can consider as some hardware. Suppose some data acquisition block like some National Instruments NI data acquisition block is there, and your sensor you can connect to the data acquisition block, and the data acquisition block will be connected to your computer or the PC. Right. So the data acquisition block, that block is the hardware block, which is basically the communicating between your sensor and the processor, or sensor and the computer. Right. So for that, typically we need some user interface software like LabVIEW kind of software. Using its GUI, you can basically that monitor the sensor data and connect the sensor data and do the some processing or logic development. So that is a very standard format. But specifically that data acquisition, that is not a very popular for your smart sensor system. We should have some other kind of communication protocol which should be integrated in the sensor IC itself. So in that regard, let us look at what kind of communication protocols are there. The first communication protocol is known as the asynchronous serial communication. What do we mean? Asynchronous means, of course, you can understand There will not be any synchronizations, and synchronization means with respect to what? With respect to, usually we refer to some clock. So asynchronous means you can consider it does not depend on any that clock synchronizations. And in this case, if we use this asynchronous serial communication protocol for connecting my sensors with processor or transmitting the sensor data to some other processor system, then it will not be synchronized with respect to some clock, and also the data transfer will occur intermittently without any continuous data transfer. Second one is known as synchronous serial communication. And there can be parallel communication and serial communication. So what is the difference? Serial means serially the data will go by bit you can consider. And parallel means, suppose 8-bit parallel means at a time 8 bits are going to the processor or to the other system, right? So there is of course some advantage and disadvantage between serial and parallel. For parallel communications, the protocol that data rate will be faster because at a time all the 8 bits are going. But serial means it will take more time to send the data bit by bit. But what is the advantage of serial communication? Here only one bit is required. So resource requirement is less, complexity is less, simplicity is more. So that's why but the speed is relatively slow. But the most of the cases we prefer the serial communication because of the simplicity, low complexity, and that low resource requirement or low pin requirement. Okay, so in this case we prefer this synchronous also. So synchronous means the communications will be synchronized with respect to some clock. So in this case the data transfer will occur in continuous stream and constant rate, and here the clock synchronization is required for transmitter and receiver. So basically you can consider the transmitter of the sensor will be connected to the receiver of the processor where I want to transmit the data, right? Or in the other way. Now based on this that under asynchronous serial communication, what is the example of asynchronous serial communication? Its example is UART protocol, right? Universal asynchronous receive and transmit. That will come under the asynchronous serial communication. In this case, what will happen? Full duplex communication. What do you mean by full duplex? Full duplex means simultaneous transmitting and receiving of data is possible in UART communication, but UART is asynchronous. It does not require any clock. And typically the data transfer rate is 20 kbps. Okay, slow data rate. On the other hand, if we go for the synchronous serial communications, in synchronous we have two important protocols. That is, one is called as the SPI, another is called as the I2C. So in synchronous, in SPI, what happened? That is serial peripheral interface. Serial peripheral interface is having the full duplex communication. Full duplex means simultaneously the data can be transmitted and received. So suppose if I consider this is your sensor, this is your sensor, and suppose sensors means the smart sensor you can say, which is integrating not only the sensor, rather the process, the signal conditioning block, signal processing block, as well as the communication block. And suppose here you have this microcontroller. So here the data transmitter, suppose here you have this TX pin and this is your RX pin you can consider. And on the other hand, here if you have this TX and here this you can consider as the RX, right? So simultaneously the data transmitting and receiving is possible. So for this TX RX, we have that SCL SDA pin is there in the IC, right? So that is basically through that pin I can basically simultaneously transmit as well as simultaneously receive. That is called as a full duplex communication. Typical data rate is quite faster. The data rate is around 10 Mbps. Okay. And device communication happens via master slaves relationship. Usually it will be having one master. For example, microcontroller is the master and many slaves, multiple sensors, displays, which will come under the slaves. That kind of configuration is possible. So serial peripheral interface or SPI communication protocol is having full duplex communication. Data rate is faster. And here we have one master controller and many slaves. On the other hand, if we go for the I2C communication protocol, this is having half duplex communication. Half duplex means what? At a time, transmitting and receiving will not take place. If transmitting is there, then receiving will not be there. If receiving is there, transmitting will not be there. So likewise, that is called as the half duplex communication, either transmitting or receiving of data at a time. Typical data rate is faster than UART, but slower than the SPI. typical 3.4 Mbps. In this case, in the SPI, we have one master and many slaves, but in this I2C communications, we can have multiple master slave configuration is possible. And usually the communications we can do with the help of the SCL SDA pin, serial data line, serial clock line, that kind of pin we can use for this I2C communication protocol. Okay, so this is about the communication protocol for the device. Okay, is it okay?
Yes, sir.
Okay. Okay. If it is fine, so then the last slide for this particular module. So with this, we are basically completing this next module where we have completed all the generic aspects of the interfacing circuits for our sensors and the actuators perspectives. Now, if we talk about that, how to integrate the sensor and IC, like in these examples here, as I said that inside this IC itself, you have the sensor, you have the circuit, everything is there. So what is that possible aspects? So we can have, suppose this is your sensor. Suppose we are using some manufacturing process, like typically if we want to that get the small miniaturized device, so then this MEMS or micro electromechanical system miniaturization fabrication process we have to go for, using which I can design my MEMS sensors, and using the VLSI technology we can design the IC. Then I can integrate my MEMS and IC together. Right here you can see in this case we are manufacturing the MEMS sensor separately and VLSI IC circuit separately, and later on we are just hybridizing both the chip, multi-chip configuration. Here we are having one chip for sensor, another chip for IC, and then we are hybridizing both the chip together, both the chip we are connecting are hybridizing together. That can be one configuration. Other configuration can be while manufacturing itself, in one wafer itself, here we are manufacturing them separately. But in the second case, you can see simultaneously we are fabricating the sensor, MEMS sensor and the IC together. In one part of the device or the wafer, we will be having the sensor. In another part, we will be having the IC. And during fabrication itself, we can get that we call as the system on chip integration. Okay, and for that here some actual schematic figures are shown, like you can see some capacitive 4 sensors are there, and so like you can consider some 3D structure. On top portions we have the sensor, in the bottom portion we have the circuit, and they are connected together so that in the one wafer itself we have the complete integrated device. Like you can see over here that in this case you have the top side, you have the MEMS sensors part, 4 sensors, and in the bottom side we have the CMOS circuit part, right? Then here again for the 3D view, you can see that here is your wafer, and in this case the left side correspond to the circuit and right side correspond to the MEMS sensors, but the fabrication is happening all together. Here again one cheap view, so that you can see in the middle portions we have the sensor, in the periphery portions we have the circuit, and during fabrications we are fabricating them all together so that I can get the fabricated device which is including not only the MEMS sensors, rather the circuit also together to build the complete integrated package system, right? So this is about the integration perspectives. Okay, so with this we are concluding this particular chapter, and now we will move forward to the CoventorWare based design simulation analysis session. So like the sensor aspects what we have discussed, the sensors working principle constructions we have learned. In our later on modules we will discuss in detail about that miniaturization fabrication process, fabrication technology, fabrication aspects, how to design it, fabricate it, those aspects. But before that, just in today's sessions we want to give you some practical idea that when you want to design some pressure sensor, force sensor, some practical sensor using this miniaturization technology, so that in small space, in few millimeter cross millimeter dimension itself, you can accommodate larger number of device and circuits together. For that purpose, how we can achieve that, what kind of fabrication process or steps are required there. So those aspects, to give you the idea and exposure to that, we will be showing you the demonstrations right now. Okay, if you have any doubts you can ask. Okay, if no questions, so let us close the session for this first session, and now we will go for the second one. So where we have Udit Narayan Bera, our PhD student is there, who is working on this MEMS based sensors and the circuit aspects. So he is having some good exposures for this CoventorWare tools and the software, which is very popular and extensively used industry grade software tools used for designing, simulating, and analyzing the MEMS based devices, sensors, actuators. So let us now start that particular session. If you have any interest, you can after going through, will be, of course, the recording is given and the slides can be also shared. And if you have an interest, you can also visit the lab and you can see his work and the other kind of different structures what has been tried out. Okay. And apart from this particular Coventor, we have another kind of software tool, console multiphysics is also there, which are also used. But anyway, so since in today's sessions, let us focus on the Coventor. So then I will now hand over to Udit to take
Yes, sir.
the Coventor aspects design part. Thank you.
Okay, am I audible?
Yes, sir.
Yes, sir. Okay. So regarding CoventorWare, the CoventorWare is one of the finite element analysis tool where the MEMS and MEMS devices are designed and simulate to get desired output. MEMS is micro electromechanical system and MEMS is nano electromechanical system. And typically we design those systems in the range of micro and nanometers. So these are the couple of uh, tools, FEA tools available in the market. You can commercially buy it, but if you look into it, that console, NSYS, IntelliSuite, Abacus, they're there. But CoventorWare is more industry application oriented because in this software you can have that how the manufacturing process happened, and you can design your own device like cantilever, your accelerometer, diaphragm, and you can have different kind of solutions there. Like I will show you. So in CoventorWare, there are mainly three steps. One, you have to select the material, like which material you are going to use. You can use silicon, you can use silicon dioxide, SU8. Then you have to go for the process, like you can go for low power, low pressure chemical deposition, or kind of sputtering, lithography. You should mention those process there, and then you will be having the layout. Like there, you have to make the 2D diagram where the 3D sensor will be built. I will show you right away. Now, these are the four main solver available in CoventorWare. Like you can go for MEMMEC, that will be used for natural frequency or pressure measurement or force measurement. Then you can go for MEM electro. You can use electrostatic actuation, or you can measure capacitance here. Then you can go for MEM PZR, that is for specifically for piezoresistivity. You can check piezoresistive effect in a sensor. Then you have the co-solve M. This is a coupled electromechanical analysis. Like here, you can see, like you can have both mechanical and electrical application coupled, and you will get a complex solution like pull-in voltage, like von Mises stress or deflection. I'll show you that. So let's get started with application. I mean, the tutorial is on micro cantilever sensor that I will show you. Now, before going for the design, you should know what are the different application of micro cantilever sensor. The micro cantilever based sensors are mainly used in different modes, as you can see in the screen. But the main focus is on atomic force microscopy or biosensor or chemical sensors in gas sensors. So this is the sensor. This is a very basic sensor in MEMS regime. People are extensively using it since last 3 decades. So we can design the micro cantilever based sensor today in front of you. This is a typical micro cantilever based sensor that we are about to see. Now, how to make this? Let's do it in the software itself. So I'm opening the CoventorWare software. I hope if you can see the screen. So this is the screen. If you have any doubt or question, you can ask me. This is the typical screen of CoventorWare, where I'm going to show you that how to build that sensor, how to make the analysis, or how to check the result, how to apply pressure and everything. One by one, I'm going to show you here. So now let's get started.
Okay. Just to add a few points. So basically, so what we are trying to say is that suppose you, I here the objective is there to design a sensor, right? So now we have discussed about different kind of sensor, that some mechanical sensor, temperature sensor, electrical sensors, optical sensor, different kind of sensors we have discussed. So just to give you the understanding, we are considering the most fundamental element of the sensors, that is called as the cantilever. And I believe that the cantilever we have discussed, like when we discussed about the strain gauge, we have shown that I have one cantilever, and on top of that cantilever, I can mount my strain gauge. I can use that strain gauge for measurement of the pressure, measurement of the force, measurement of the torque, and so on. Is not it? So that we have already discussed in detail. Now we will show that suppose if I want to design that kind of some pressure sensors, cantilever based pressure sensors. So for that, first I have to design one cantilever, and then I have to deposit some piezoresistor, for example, and then I have to see that now before that suppose while designing the sensor, first what I need to know that what application I am targeting. If my application is to measure the pressure in some that boiler or some industrial that design or industrial plant, or for some health monitoring purpose, some blood pressure. So what kind of pressures I am targeting? Based on that, I need to decide what should be the range of my pressure which I need to measure, because we are already aware about the static and dynamic characteristic of the sensors. The sensors can have different sensitivity, different range, different resolutions. So which will be requiring my purpose. So first I need to know that what kind of application I am targeting. In that application, what are the different values are required. What are the typical range I need to measure, resolution required, sensitivity required, those things. According to that, I need to design the sensor. Now, before going into the actual fabrication, first I need to design it using some software tool, and then in the software tool itself, I need to do the detailed analysis. Because in the fabrication domain, I cannot, suppose once I fabricated some randomly, then again I am checking it for the practical application, that is not serving my purpose. Then again I am redoing it. That is not possible, or that is not feasible also. Unnecessarily that will waste my time, resource, effort, everything. Economics points of view also it will be violated. So that's why first we will be doing everything in the simulation. And for simulating the things, first you need to choose that what should be your dimension. You have to have some idea that what will be my length, weight, thickness, the geometry of the structure. Then what material I am essentially requiring to design it, whether I should go for silicon or aluminum or some other metal. So I need to know the metal. So that's why in the one of the slides he was showing that what are the steps. So first you have to choose the dimension geometry, then the fabrication point of view, you have to choose what is the metal, then you have the dimensions. Then after doing that, you will be designing that in the software tool. After designing, how to analyze it. So this kind of the designs, if the designs are very complex, then we cannot get some analytical closed form solutions for the analysis purpose. For that purpose, mostly we try to do some numerical simulation. So for numerical simulation, what we do, suppose if I have a full cantilever, then I segregate the whole cantilever in suppose n number of small parts. that what we call as the meshing. And for each individual part, we do the calculation. That is simply, you can consider some F equals to Kx. If I have some that mass spring system where I apply some force F, then the corresponding spring restoration force will be Kx, is not it? And F will be equals to Kx, where F is the force, X is the displacement, K is called as the stiffness matrix. And root over m by k, that correspond to that root over your k by m, so that correspond to your natural frequency. So from that perspective, we come up with the stiffness matrix, stiffness parameter or the mass parameter for an individual element. Then I consider for the whole cantilever, I assemble all the individual components together to get one n cross n matrix kind of things to do the analysis. And for that purpose, the very popular numerical method which are used for analyzing these kind of devices is called as the FEM or finite element method, where the whole cantilever we segregate it into finite number of individual elements and we do the analysis for the individual element. Then later on we assemble the whole analysis together to get the complete solution, right? So that's why our step will be that design, coming up with the geometry, then the material choosing, then the fabricating the device, then you have to use some solver to solve it. That if I apply 1 Newton pressure, then what will be its corresponding displacement, stress, resistance change, those things. So for that we need some solver using which the solutions will be taking place using the FEM based techniques, and then finally we will be getting the output and you can see the output. Now by checking the output, you need to decide that whether that output is proper or not, whether with that output I can go ahead or not. If you are satisfied with the simulation performance, then only you will go for the actual fabrication, right? So that will reduce your effort, cost, time, everything. So that's why we are trying to give the exposure with respect to these beautiful tools using which you can do the complete design, analysis, simulation, every perspective. Okay, so here these are the different kind of solver. For mechanical analysis, we have to use this MEMS solver. For electrical analysis, we have to use this MEM electro. For PZR or this piezoresistance based analysis, we have to use the MEM PZR solver. And co-solve means this is basically helping you to that combine the multiple domain together. That coupled physics, coupled analysis, where electromechanical means both electrical part as well as the mechanical part. Likewise, coupled analysis is possible, right? So I hope you have got the background. Yeah, please carry forward.
Yeah. So before building it, let me show you the 3 different steps here. First of all, first is material. So here you can see that we have a lot of material options, but let me show you how it looks. From here in CoventorWare, you have the material database, like there are like aluminum nitride, silicon, PZR. There are many materials available, and their properties like density, stress, piezoresistive coefficient, and everything is mentioned here. So you can use any material from here. That is one option. Second option, you can import a new material where you can edit the property of these. Suppose you want to use one different kind of material that is not available here, although most of the materials are available here. uh, but you can still bring new material and edit your property, and you can use it here. In this design, I'm going to use either silicon or polysilicon, so they are already available here. Let me show you that. Let's say this is the polysilicon. So you can see here that that elastic constant, that is 160 GPa, Poisson's ratio, everything is mentioned here. So I don't need to edit it here, but you can see here that is the piezoresistive coefficient. It is mentioned where the values are already I have put here, but when you will be first time using it, these values were not there. So you can edit it. So the point is, CoventorWare will give you a very, very flexible material handling database where you can use any of the materials for your cantilever or any other the sensor you are going to make. So okay, now come to the next part, that is process. So although it was already mentioned from beginning that what are the process I'm going to do, but step by step I want to show you. The first one is substrate. As you know that you have to start the process with a substrate where, I mean, uh, it will be a typical silicon wafer where your cantilever will be made. So let me show you that how the substrate will be looking like by disabling other steps, so that one by one you can check that how it will look like. Okay, if I build this, you can see that the first layer will be the substrate. So this is what exactly the first layer. This is, let's say, a typical silicon substrate you have. The layout editor I will show you a little later, but for the time being, this is the first step you have taken. That this is the silicon wafer and this is the substrate. Now, in the second step, what I'm going to do, I'm going to this is called a passivation layer, because we need this passivation so that there will be one electrode on top of it. So I need to passivate it from the substrate. So let's enable this, and then if you build it again, so you will see another layer. You can see above substrate there is one passivation layer I have deposited here, a passivation. This is Si3N4. This is the passivation layer. Now, in the next step, what we will do, we will be having now the electrode part. That electrode part that is made by polysilicon. You can see the different steps are having all the thickness and other parameters mentioned. Like in this step, it is LPCVD, like low pressure chemical vapor deposition. That's the process. That's the process. And the name of the material is polysilicon. That is, I mean, the layer name, I am telling it electrode here. So it is a polysilicon, and you can see the thickness. Now you may ask that why only thickness, where from the length and width will be coming. In that case, let me show you. There is a layout editor that I was about to show you. You can see here in layout editor, we have different things made from the beginning only. You can do it later also. Let me tell you, this portion I have, if I double click it, you can see here that this portion I have mentioned is as electrode. That means I will be growing my electrode in this region only. Similarly, if I double click on this yellow portion, it is written as make zero. So this is a kind of mask. I'm coming back to it, but I will be my cantilever beam will be in this region only. So in this layout editor, you will be having the dimension, like you can see here that the length and width, you can mention it from here. So you can build the 2D layout in this layout editor, and in process editor, you can have the thickness so that you can build the 3D model or solid model. Okay, so get back to that process where the silicon deposition, the electrode will be there. Now let me show you that how the electrode will be looking like if I rebuild it again. So once the polysilicon is deposited, hold on. Okay, the processor is looking little busy. So by that time, let me complete the rest of the steps. So after that electrode portion, then we'll be having some dielectric level. They have their own purpose. I will get back to you. I am not going in all details. So let me enable them so you can see that how the exact output model will look like. Then I will be showing you that how the process has done. So yes, after doing that, after going through all the processes, this has happened. Now, one by one, let me link with you. You have seen the substrate level in the below already. Now, above that, that red portion was passivation layer. Now, how come this this electrode portion you can see in the here, if you look at it closely, that electrode is not fully covered on the top of the surface. It is just this position. Now here I want to show you that how you have got. Can you see here that this green portion was electrode? This green portion was electrode. That's how my mask was set. Now here I need to tell you that what is mask here. The electrode was deposited. If you look into this structure, electrode was first deposited totally it was deposited first. Then what happened? Then I have set a mask in this layer. In layout editor, I have set this mask with a photoresist plus. Photoresist plus means the mask, where the mask will be there, rest of the portion will be etched away. Etched away means the UV rays, the UV light will make the other portion solvable, and that will be etched away, and this portion only, the remaining portion will be only kept. So that's how I have created this portion, this electrode portion. In the same way, the cantilever was also built. Now let me show you, since the processor is now okay. Now let me show you the next step. That is, when the oxide and the dielectric and electrode layer was already done. After that, how we have grown the electrode. Let me disable this. Okay. Now, after the electrode and after the dielectric, what I am going to do, I am going to rebuild it again so that you can see. Yes. Now you can see that after the substrate, above that was the red color, that passivation layer. Above that, it was electrode and dielectric, and above that, this yellow portion, if you can see, this is a sacrificial layer. That means we will be developing the cantilever on top of it. And after the development, we will be etching it out. Etching it out means we will be deleting it. So this is the sacrificial layer. So once the sacrificial layer was done, so the next step is your uh, the cantilever, the cantilever should be there. So that aluminum sputtering, that and RI each, that I have already told you, that will be, let me enable it first. So here the cantilever is made up of aluminum. You can also change it from here. The material you can change it. Although it is aluminum film, is in the tutorial already. So that's why I'm using it. Otherwise, you can use it as silicon also. So once the aluminum sputtering I am using here. So let me show you that how it will be changing. If I build it again, yes, you can see here that above that sacrificial layer, above that yellow portion, the cantilever, the yellow portion is already we got. And if you can see one hump here, that is the portion we call it anchor. Anchor means the fixed end of the cantilever, because the cantilever beam will be fixed here and the rest of the portion will be hanging. I mean, it will be a free end so that you can use it for vibration or other purpose. So now in the next step, what I will do, I will I will I will deposit the cantilever material over here, and so that you can see, so that you can beat the cantilever. So now in the process, let me etch away the. You can see the make zero. Let me show you why this make zero. What I am saying by make zero, in the layout editor, I have shown you this yellow portion. This yellow portion was make zero. What is this? This is the mask. This is the mask where cantilever will be there. Your cantilever is now all over the substrate, but you don't need your cantilever to be all over the substrate. You need your cantilever to be here only in this position. So this make zero was used for that. Okay. Similarly, in the process also, you can see that in this portion the make zero is there. So when this process will be done, then your only cantilever you will see right now. Let me show you that how after this step, how your cantilever will be looking like. If I rebuild it, yes, see, after make zero, I mean, after that mask, so this is that yellow portion is your polyimide that will be etched away later. But now you can see your cantilever is already grown on top of that sacrificed layer, and your one portion is already fixed. That's your cantilever. So what will be the next step? So the next step will be this yellow position, this yellow portion that I will be etching away, so that you can apply force and other thing in this free end. So let me show you in the last step, that release etched. What is that? Etching is a process. Etching, I mean, in a MEMS device fabrication, etching is a process where we typically delete or etch away the layer. So let's do that. So in this step, what we are doing, we are etching away the polyimide. That yellow portion now we will be etching away. So if I rebuild it again, so then you will see that your polyimide portion will be etched away. See. So this is now your cantilever. And you can see that according to the mask, this green portion is your electrode, your blue portion is dielectric, your yellow portion is your cantilever, exact cantilever that is grown over the substrate of silicon. So this is the full cantilever model you have after the layout and after the process. So let me show you the layout once again, how it is related. You can see here, let me zoom it. The outer surface is the substrate. Here, the green one, they are the electrodes. You can ask me why these two electrodes. There are one is a sensing electrode, another one is actuation electrode. That's why there are two. This portion is for anchor. You can see there was a hump in the design. This portion, I mean, in anchor side, if you see, this portion is fixed. To make that fixed point, we have purposefully used that mask here. This is for anchor. If I double click, yes, you can see this is the anchor. So let me show you here that how they are the photoresist, how the mask is there. There are substrate, electrode, anchor, make zero. These are the these are the masks we have used for different purpose. Yellow one is for our cantilever, that is make zero. You can see the photoresist is plus. So that's how the mask design and 2D layout we made it in this layout editor. And after that, in process editor, we define the processes. That what are the processes? There are many other processes. If you go here, you can check with, there are a lot of processes available for different types of fabrication. But for the time being, I'm only explaining that how cantilever can be made. So you can see mainly there are that CVD, PECVD, that is, and other etching. Total 3-4 processes have used here. So in detail, you can go through these processes, but for the time being, you just know that this CVD, and they are all thin film deposition technique, where you can deposit to make some thin film like sensors. Okay, so here is your sensor. The sensor is built on a top of substrate. Now, what you need to do before going for solving, you need to mesh it. As Sir already told you that to go for finite element analysis, you need to set you need to divide it in a very small parts with boundary conditions, so that, I mean, the governing equations will be applied and you will be getting a better result. So that's the process. We call it meshing. Meshing means we will be breaking it into different parts. But for that, let me hide these two steps first, so that now you can see that your cantilever is looking like this. I'm hiding the substrate and passivation because they are not in the part of simulation right now. So we'll be only concerning about this mechanical layer and your electrode and anchor and dielectric. Okay, so for meshing purpose, let's take the electrode, dielectric, and mechanical part into add them to the mesh model. That's how we can add them into the mesh model. After that, what you need to do, you need to set the properties. Let's go to the electrode property. Its name is electrode, okay. And now go to the property. You can also change material from here. I mean, it will be the final time you can change the material if you wish to. Okay, so this is electrode, so make it a conductor because it's not dielectric. And you should click this point as well. Why? Because it is written suppress except for MEM electrode. That means when you will be, I mean, when you will be working with the actuation voltage or current, then you should use this electrode. But otherwise, if you are your micro cantilever is operating only based on the force or pressure you are applying, then this electrode should not be in the picture. That is the meaning of this line, that suppress except for MEM electrode. In MEM electro, we will be only concerning about the actuation voltage and all. In other cases where mechanical forces will be used, we do not wish to simulate this for the purpose of time. Okay, so let's click OK, then go for dielectric, then again check it is dielectric. Also make sure that it is suppressed except for MEM electro. Okay, now come to the fourth layer, this one. So you can set, you can similarly, I am not changing it for MEM electro because this is the main part. So let it be as it is, no problem. So these are the basic property we have set. But for the simulation purpose, you need to assign some name to this model, to some parts. For that, what you need to do, you can see this portion, that what I was saying, anchor should be fixed. So make sure this portion is fixed. So for doing that, I need to give it a name. Let's name it as fix. I'm keeping it as fixed. Okay. So this side is now named as fixed. Now the next one we will be using that the top surface where we will be providing the pressure. So let's take the name as, let's put this surface as top. So let's set the name as top. Okay. Now another thing we will be required in this simulation, that this is your actuation electrode where you will be applying the voltage, so that there will be an electrostatic force that will be attracting the cantilever down. So this one, let me point it out. This one, let's take the name as actuation electrode. Actuation electrode where we will be providing the voltage. Now you may ask that why I am not naming the others. Naming the others means there are, this one is sensing electrode, and the other in the top, this one is the in the top, the blue one is dielectric. I am not naming it because for the time being we don't need it, but sometimes whenever it is a good practice to name all of them, all the phases, that you can do also. So main portion I have already done. Now, after naming it, what you should do now, you should go for the meshing part. Let's take the region 1 and go for the mesher setting. What I am going to do, I am going to take a Manhattan bricks. This is a very popular, that Manhattan bricks, not only because of popular, but we also take this bricks model because in CoventorWare, the bricks models gave the probably the best solution. And in when you will be going for piezoresistive analysis, you must have the bricks model analysis. Otherwise, the piezoresistivity main piezometer will not work. That is the two reasons we use for Manhattan bricks. And element size, I mean, how much smaller element you want to take. Let's take for the timing, let's say in x-axis, in y-axis, I am taking 2, 2, and in z-axis, I am taking 1. You can ask me why these are 2, why this is 1. These are 2, that is a normal, 2 is a normal number I'm taking, but this is 1. Why I'm taking? Because in this cantilever, when you will be applying force or pressure, it will be bending downwards. So it will be having a kind of one, I mean, z-axis bending. That's the reason I need a fine meshing in z-axis. No other reason. You can go for all of them 1, no problem at all. So let's take this 2 to 1. And in region 1, again, I am taking the same one, that is 2 to 1. 2 to 1. Okay. So the moment you have already taken this cantilever beam as in mesh model, so what you need to do, you need to mesh it. So you can see now your cantilever beam has been broken into small pieces. I mean, the analysis will be done in these pieces, in these boxes. So now the common sense, the more the fine meshing will be, the better the result you will get. That means I have taken 2 to 1. If I just change it, the measure setting, let's say this is 2 to 1 is now 1, and let's take it here 1, and let's take it here 0.5. I'm making these block size a bit smaller. So measure setting, let's go for 1 here, and here 0.5. Okay, and then if you do this meshing, you can see the block sizes are small. So if the block sizes are small, your results will be better, but at the cost of time, definitely, because the more the fine meshing will be, the more time taking it will be. I mean, it may require more than 1 hour sometimes to do the solution, to do the simulation. Anyway, I'll be going with this only, no problem. So your meshing is done. In the meantime, if you have any doubts or question, you can ask. So, so if the meshing is done, the next step is to go for the solver. So what are the things I can solve here? I can get the result from. Okay, so just close this model and then go to the Coventor here. So we have this one we have already seen. This one we have already meshed right now in front of you. Okay. So to solve that, what are the things you can do? You can right click it, and you can go for new analysis. If you can say new analysis. So when you will be going for new analysis, you can see there are Coventor solver opened. One is MEM electro, another one is MEM make. That's the same thing I have shown you in the slides. Okay, so let's start with MEM make. Here you will be mostly doing the mechanical things. So next, what I'm going to do here, let's take the natural frequency first. So I'm selecting the modal analysis, and I'm saying the number of modes are 6. For better performance, I'm choosing it 12,000, the memory solver, and that's it. But before going for the solution, you must set the boundary conditions, like what I told you, that when your cantilever will be working, that anchor will be fixed. So what I am doing, I am just fixing that fixed position. If you remember, I have given the name fix at that anchor position. I'm just making it fix all. That means in XYZ condition direction, that will be fixed. That's the boundary condition I have given. Okay. So this will give you the natural frequency. Let's run it, and let's call this as modal analysis. Okay. So the moment I did that, so it is showing, it is running. You can also check the progress here, or in the log view also you can see the progress. Now see that it is completed. Now let me show you how the results are. Okay. To show that results, what is the natural frequency? You will get it right now here. Yes. From here, you may see that it is giving you that 263 kilohertz, almost like it is giving you the modal frequency. By the way, let me tell you the dimension of this cantilever is 40 micrometer by 6 micrometer by 1 micrometer. So that is the reason the value is giving. So this is the modal frequency. Now let me show you the results section, that how the 6 modes are different. I mean, the bending, if I stop, the bending is different for different modes, but we normally, for resonant frequency, we only choose the first mode, so that this is the modal frequency. Okay. Now the first result, I hope you got the point. This is the resonant frequency we got. So after that, what we will do, in MEMMake only, will be doing the different solution. Like go to the same MEMS model, and in that MEMS model, go for new analysis again. In MEMS, go for next. This time, I am not going for nodal analysis. Now I am going to apply some force. So for that, what to do? For that, let me go to surface BC, boundary condition. I am fixing the first, uh, I am fixing that kind of anchor. Second boundary condition, use load patch. Let me apply some pressure. Where? In the top. Can you see why I have given the name fix and top? Because I will be applying some pressure because I have to simulate it. So at top, here you have two options. One, you can use constant value here, or you can have a parametric study, or like you can have variable where you can check a range of pressure in a single time. But for the time being, let's say I'm using 0.025. This is the megapascal range of pressure I am applying here, 0.025. This is the force, this is the pressure I am going to apply on top of the cantilever. Okay. And now I am running it again. And let's say this is pressure. This is pressure. So it has started. You can check the progress from here. So as I have done the meshing a little fine, that's why it is taking little bit time. Otherwise, it would have been done more faster. So let's check the result. Here, I mean, in make domain, you can also see here also the displacement, but it will be better to see that what is the displacement and what is the stress generated. Now, plot, go to contour plot. Here you can select displacement. See, from here you can see after applying 0.025 megapascal pressure on top of it, the deflection, the maximum deflection of this cantilever is 12 micrometer, 1.2 into 10 to the power 1. Yes, of course, it is out of range because I have used the pressure was high. But for here, you can see that how this is. I mean, as you know, the fixed end will be having a very less deflection, and the free end will be having the maximum deflection. So, and this contour of color, you can see from here that how the deflection, the bending of this cantilever is not linear in nature. So it is changing from here to here. The maximum bending is at free end, that is here, and the minimum, and it is almost zero. It is zero because I have made it fixed. So it is in the this fixed end. Similarly, you can check the stress, that where the stress is generating. So for that, you can see it is exactly opposite to your displacement or deflection. Like the pressure or the stress is very less, almost near to zero at free end, but the pressure as in fixed end, it is very high. So you can see that red color is giving you the idea that if you are going to make one piezoresistive cantilever, then your piezoresistor should be placed in this red region only, so that your piezoresistor will be experiencing more stress to get the better sensitivity, del R by R. So, but if you put your piezoresistor in this blue region, you will hardly experience any stress, or there won't be any change in resistance. So this is a von Mises stress we normally use in MEMS. So that's how you can check the stress contour, surface stress contour, or the deflection contour. So based on the MEMS solver or applied pressure, you can get this. Now, also you can check different places. Like if you have a probe option, okay. So if you put your cursor here, you can see the result in the right side. So you can see at red point exactly what are the stress, and in this section, in this blue section, what are the, I mean, the stresses are very small. Okay, so this is MEM-MEC. Now, after that MEM-MEC, let's go to MEM-Electro. MEM-Electro will be, there are two, we'll be looking at two possible solution. One is to, if time permit, I'll go for capacitor. Otherwise, I'll show you that how after applying that electrode voltage, now I will be applying the voltage. So let's say we need to find out force on conductor parts. That means when you will be applying voltage, there will be a electrostatic force the conductor will be experiencing, that your cantilever will be experiencing. Okay, that's why I have selected force on conductor. And this part for betterment, let's go for T. I mean, this is for the iteration. I'm selecting it, no problem. The next here we will be selecting some different kind of uh, boundary condition, that is conductor conductor boundary condition. You can see here the conductor 0, conductor 1, conductor 2. Okay, now the problem will be if you don't know that which one is actuation electrode, then you will be, I mean, by you will be mistaken that where to use that uh, voltage. So for that, let me show you the meshed model once again. So here you can see, from here you can see your, if I choose the face, yes. So conductor 1 is your actuation electrode, and conductor 2 is your sensing electrode. So you have to apply the voltage at conductor 1. Okay, so let's go to the Coventor, go to conductor VC. Conductor 1 is your actuation electrode. Let's apply 1 volt here. Okay, and okay, nothing else. We have already applied 1 volt, and if you want, you can check that fix is there, no problem. So let's run it. So, electro. So the progress, you can track it here. In MEM electro, we are not applying any external force or any external pressure. We are only applying the electrode voltage, so that the actuation is done by that electrode voltage only. In MEM-MEC, we have used the external pressure. Okay, so you got the that the simulation is completed. So let's check the answer, view result. So what are the things you can get it from here? You can see that from here, that is the charge. Now let me show you the force on conductor. Yes. So from this table, you can see that in conductor 1, in Z direction, if you look into it, you can see that micronewton force is getting applied to your cantilever when you apply 1 volt to your cantilever. That's the meaning of this point. I mean, when you are applying the electrode voltage, your micro cantilever is experiencing that force and it is bending down. So let me show you. Okay, here. So these are the 4 steps. If you want to know that why these 4 steps are there in MEM electro, just a couple of minutes ago I have shown you the refining level was 3. That's the reason, that is step 1, 2, 3, 4. So from here, from MEM electro, you can find out the force actually. Okay, the electrostatic force. Okay, using this MEM electro, also if you want to do the same again here, new analysis, and go for MEM electro, and then you can use the capacitance matrix. Like if you want to check the capacitance between the electrode and your between your kind of cantilever, then also you will get the different kind of result. I mean, you can also check the capacitance level in using this MEM electro. I'm not doing it, performing it here, but that is also possible. Now, the important thing, that is the co-solve that we will be doing right now. So for that, what I am doing, let's take the open new co-solve. Okay, you can see in this case, you have both MEM-MAKE and you have both MEM electro. That is, this is the coupled field. I mean, it is a mechatronic, like you have your mechanical boundaries, you have your electrical boundaries as well. So in MEM-MAKE, so what I'm doing, let's take, it will take a little bit more time. So I'm enhancing the solver memory power a little bit. It was already 12,000. And then let's go to MEM electro. And here I'm reducing, let's make it one only, not three, so that the time will be taking less. And then you can see there are more boundary conditions than separately MEM-MAKE or MEM electro. So let's take one upon one, one by one. So if you remember which one was electrode, if you remember here, this one, conductor one was electrode. Okay, so accordingly, conductor one is electrode. So let me apply 1 volt starting, and I'm making the variable name is voltage one. What I'm trying to do now, I'm trying to apply a series of voltages starting with 1 voltage. So it is of, let's take it voltage one. Okay, now dielectric VC, you don't need to do anything. Okay, so let me open another model, because I need to show you something else. Model. Just hold on a second. Yes. So how to do that? Let's take this new co-solver. Yeah, the MEM-MAKE, I have already done it here. I've shown you the MEM electro. It is already selected. Let's take it to 1. Boundary condition, that is 1 volt. And here, let's take it voltage. Okay. Now, likewise, and then you can go for run. I'm not doing it because I mean it will take a lot of time, but I can show you that I have already done that simulation previously, so I can show you the result, but how it will look like. Open the results, so that here, what are the things you can check? Here you can check the force on conductors, the pull-in voltages, and other things. So one by one, let me show you that how the pull-in voltages looks like. So in the result, you will see the graph. Yes, here is the graph generated by the Coventor. Here, let me give it some meaning so that you can understand. Yes, I hope you can see the graph. This is the pull-in. You can see that actuation voltage, the actuation voltage, it was changing from 0 to, let's say I have given it up to 10, but before 7 only, pull-in means after some time that the cantilever will be pulling down. I mean, it will be, I mean, it will about to touch the that anode, that electrode. So, so that is the instability limit. I mean, after that, the cantilever will be no more in operation region. So this is how, I mean, when you are changing the voltage, your pulling is changing. Okay. Similarly, if I show you here that the pull-in voltage summary, so in this graph you can see that the displacement was there, but after some 6.5 volt, it has started converging, and at 7 volt, it has already diverged. Okay, that means your pull-in range starting from the lower bound of your pull-in is 6.5 volt and the upper bound is 7 volt. That also you can check it from here. Okay, this is your pull-in limit. So that's how you can get the information about pull-in. Also, you can check the electrostatic, I mean, information. Electrostatic information means the deflection and the stress, the everything due to this actuation electrode. So how that will be looking like if I select Coventor result selection. Now now you can see according to the change in voltage how the deflection is changing. Okay, so that's how you can check the displacement and the stress also. From here you can also check stress. You can also measure some other things also. Okay, so in co-solvent you can mainly check for pulling or the deflection and stress also. That's a coupled solver. So mainly you have just now have seen the three solver. One is MEMS, another one is MEM electro, and the last one you have seen that co-solvent. So once these are done, let me show you that if you have a piezoresistive cantilever, very quickly, I will take 5 more minutes. Here, this is another cantilever, similar cantilever, but you can see if I zoom it, that there is a black layer on the top of your cantilever. This black layer is nothing but your piezoresistor that is made up of doped silicon or polysilicon. Now, the first question, why is it here? Because you have just now have seen that the maximum stress is in this region only. So that's why the piezoresistor is placed here. Okay. So how the piezoresistor, I mean, how this kind of solver work? If you go, let me show you one solution so that you can see that how the piezo in piezo domain, how the results are shown. You can see I'm not showing you exactly, I mean, what are the different steps in making that piezo, because it will take little time. But in piezo resistor, you can see that what are the changes in current after applying your voltage. After applying your voltage, very quickly, let me show you that how that voltage was applied. You can see it here. If I analyze, if I show you the piezo resistor only, this is your piezo resistor. Let me zoom it. This is the piezo resistor. Now let me show you that how the stress or current or things are with it. Okay, that's stress on Mrs. Stress is here. Okay, you can see that's how your piezo resistor is experiencing the stress. But in MEMPZR, what you are supposed to measure, the change in voltage or change in resistance. So let me show you that what about the current density. You can also check the current density here. Okay. Also, you can check that voltage distribution. It was here. Is so that's how you can check the different types of piezoresistive effect. I mean, the change in voltage or change in current. Now, how these things came? If I had already made it. So if we can just show you that the solver setting, how it works. See, the let's go to the next. Yes, here you can see that in piezo register, in this piezo, in these boundary conditions, that I have applied two voltage. One is 5 volt, one is 0 volt. If you remember the model, you have seen that your piezo was having here in this model. If I zoom it, you can get it that it is only one. Okay, so one patch I am using 0 volt, one patch I am using 5 volt, so that it we will measure the change in current when there will be a change in stress. Okay, so that's how here one is 5 volt, another one is 0 volt. That is our surface boundary condition. And about the volume boundary condition, you can see that I am assigning that piezo portion as piezo part. That's it. Okay, so that's how I used to run the piezo solver, and you will get that kind of result. So if I get back to this, you have seen this MEMS. This MEMS was, let me show you a couple of results that you have already seen. See, this MEMS is for your natural frequency or your pressure application. CoSolvem is for your Boolean voltage. I've shown you in this figure. You can show that MEMS pieces are, this is MEMS piece data, this is the voltage distribution, and this is your current density distribution. In MEMS electro, you can also check charge distribution, and these are the results you have already seen. So using CoventorWare, you can easily you can design a cantilever sensor, you can modify it, you can deposit piezoresistor in your own style. There are many styles available. I mean, you can design your own piezoresistor and you can simulate and get the result. Now, why you should use CoventorWare? Because it will give you a fabrication awareness, first of all. Second, it will give you a better performance. And third, it will have a different kind of environment where a specific job can be done better way than other commercially available software. Like that coupled analysis is better than ANSYS. So these are the reasons we should go for CoventorWare. And I wish that you get a little bit of knowledge. It is not possible for me to give you entire knowledge of CoventorWare in this small period of time, but I went little faster. But I hope you got the point that how it was started from material to process to layout to solid model. After solid model, we go for the meshing. After meshing, we go for the different solver. Of course, all the solvers are having their own different boundary conditions. When you will be working on it, you will be used to it. You will be used to it. So right now, it might look like the boundary conditions are not so friendly, but once you will be working with it, it will be very very easy. So with that, you will be getting the solver results, and then you can match it with your conventional uh, formulas, and you can do that. Okay, so if you have any question or any doubt or anything or any suggestion, you can definitely share with me right now, or else it's all that's all from my side. Thank you very much for patiently listening. Thank you, sir, for the wonderful opportunity to speak here.
Yeah, thank you, Udit. Yeah, so students, yeah, so of course, as you understand, so this is a very that sophisticated tools which is giving exposures from different aspects, and you can understand that within 1 hour, the complete until you do your hands-on, the things will not be clearer that much. But still, we hope that you got some exposure and some ideas that what this tool is all about and how practically we do the design for the MEMS sensors, considering this cantilever as an example. And all these details like the process steps like that wafer, deposition, mask, this lithography. So those kind of things or terminologies what is discussed over here in our we have one dedicated module in the course where we will discuss in detail with lot of diagrams and conceptual ideas. We will discuss them, but this is to give you the idea. We have just shown you the demonstration. So I hope that with this you have got the idea that how the thing goes on and how the what are the challenges aspects and what is the approaches. So I hope that thing is clearer to you now. Once you venture into the field by your own and try to do practicing, then the things will be much more clearer. But at least for the time being, we hope that you have got some overview and idea about the approaches and aspects for the designing, analysis, and the simulation perspectives. Okay. So if you have any doubts, you can ask now, right? Ask us right now, or later on also you can visit our lab by contacting Udit to see his actual structure and the things. So yeah. And apart from that, we have another. This is since bit heavy cost and heavy extensive software. So we have that another software is also there, COMSOL Multiphysics. That is also widely used for generic simulation purposes, but the fabrication flavor is not there. So anyway, so as per your interest, please feel free to contact us, and if you have any doubts, you can ask. So if no questions, so then we will close the session. And of course, this is recorded, so you can refer this later on also as per the requirement. Okay, so thank you so much.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.